by A Mattioni from the University of Bourgogne-Franche-Comté, Besançon, France. And he will be talking on energy-based robust control of nonlinear port-Hamiltonian systems.
Okay, thank you for the introduction. So in this presentation, I will first talk about the research results that I had in these first 2 years of ConFlex project. Then I will list the publication that I have, and then the secondments, the training and the outreach activities that I did in the same period. So the motivation of my work is coming from a project in collaboration with the non-beneficiary partner Thales Alenia Space, where they had to design double manipulator for the retrieving of space debris that are orbiting around the Earth. So this is a problem that have multiple problems inside that we decided to split in different parts. So the first problem that we try to solve is the modeling, an analytical modeling of the double flexible manipulator. Flexible because the manipulator for spatial application is normally built with lightweight materials that will present some deformation during the normal motion and especially in contact with external objects. So we first did the modeling of the double flexible manipulator in the port-Hamiltonian framework. Then we studied 2 different control laws that allow to dump the vibration coming from the flexible deformations. For a simple model, there is the one of a single flexible rotating link, and the work and that it's ongoing in this moment is about the impact scenario of flexible beam with external object. So we start with the double flexible manipulator model that has been published in a applied mathematical modeling journal. And for this model, we assume we have used Timoshenko assumptions for the flexible beams, and in the paper we show that the overall model can be obtained as the power preserving interconnection of 2 sets of PDEs that describe the dynamics of the flexible beams with a set of ODEs that instead describe the rigid motion of the joints. We show then that the overall system can be written as a semilinear operator equation with input corresponding to the torque applied to the first and second joints and the output corresponding to the angular velocity of the same joints. Then we show that the system is passive with respect to the internal energy E, in the sense that the derivative with respect to time of the energy along solutions it's equal if we neglect the dissipation inside the mechanism to the product between the input and the output that I previously defined. Then at the end of the paper, there is also a structure preserving discretization that's allowed to obtain a finite dimensional port-Hamiltonian system that can be used for simulation purposes. Then for studying the control law for accounting of the flexible vibration, we prefer to use a simpler model, and for this purpose we use a single flexible rotating beam, of which the model can be obtained always with a power preserving interconnection with a infinite dimensional port-Hamiltonian system in 1 dimension with a finite dimensional port-Hamiltonian system that describes the dynamics of the hub on which the flexible beam is connected. So the system can be written as a linear boundary control system, where the state is defined as the composition of the flexible beam state and the rotating hub states. For the control design, we have been inspired by the work of Luo of the paper of the 1999, where the control law is basically composed by 2 parts. The first part is a PD controller that's allowed to orientate the beam in the desired orientation, and the second part is composed by the product between a linear function g of z, that is a linear function of the flexible beam state, that multiplies a controller state xc. In this case, the controller state xc is dynamic, and it's dynamic. It's defined by basically two terms. The first term is a dissipation term, and the second term is obtained by the product between the same linear function g of z with the angular velocity of the hub on which the beam is connected. And a similar control law as will be presented in the IFAC World Congress, where instead of using the original flexible beam state, we use a reconstructed beam state that is coming from a boundary observer. But for this control law, it is possible to show that the closed loop equation, it's a semilinear operator equation, where the state is composed by the flexible beam state, the rotating hub state, and the controller state. And it can be shown that the system is well posed in the sense that the solution exists and is unique, and it continuously depends on the initial conditions. And it's also possible to show asymptotic stability using perturbation theory. So first, it is necessary to show that the operator A is the infinitesimal generator of a contraction C0 semigroup in the state space that we are considering, and the nonlinearity is square integrable along solution. With these two ingredients, it is possible to conclude about asymptotic stability of the closed loop system. The other control law that we studied, it always used the linear model that I introduced before. And in this case, we take inspiration from a control law proposed by Morgul in 1999 that was proposed for a one-dimensional wave equation. So as before, the control law is composed by two parts. The first part is a proportional derivative parts that, as before, it is used for orientate the beam in the desired orientation. And the second part is a so-called strong dissipation feedback. This strong dissipation feedback is defined as the time derivative of the output operator from an output operator of this of the PDs that describe the flexible beam. In this case, in this particular case, the boundary condition that we are using is the restoring torque that the flexible beam apply to the hub on which it is connected. So in the control law, we take the time derivative of this boundary condition of this boundary variable, and we apply directly on the finite dimensional part of our system. And with appropriate change of variables, it is possible to show that this strong dissipation feedback actually corresponds to a boundary dissipation directly on the PDEs of the flexible beams. And it is possible to show that the closed loop equation corresponds to an autonomous linear operator equation, and that the operator A, it's a contraction, generates a contraction C0 semigroup in an appropriate weighted state space, where the inner product is defined as the sum between the original energy of the flexible beam and the awaited energy of the rotating hub in the new coordinates eta. And the weighting parameter alpha depends on the choice of the controller parameters of the PD part of the control law. Then it's also possible to show asymptotic stability of the closed loop system using the LaSalle invariant principle. But for that, it's necessary to add an assumption on the approximate observability of the rotating flexible beam that in this case has been shown in the previous literature that is an assumption that holds. Part of the ongoing work is on the extension of this control law to a general one-dimensional port-Hamiltonian system connected to a finite-dimensional port-Hamiltonian system with input on the finite-dimensional part, where we try to relax the assumption on approximate observability and try to use the properties of port-Hamiltonian system to assure this assumption, to prove this assumption. This work has been submitted to the Control and Decision Conference of this year. The ongoing work, it's focusing on the impact scenario. So for studying the impact scenario, we take a model that is similar to the one that we studied before, but differently as an end effector that has an inertia, a mass, and is the end effector that enters in contact with the external object. The external object is modeled with a soft impact model that is composed by a linear spring and a nonlinear damper. The damper is taken to be nonlinear, taking inspiration from previous literature on the same field, and the nonlinearity of the damper helps to conclude about well-posedness of the system. This because with this nonlinearity that depends on the deformation of the object on which we are entering in contact, allow to have a friction force that is continuous in time. This, for example, try to think about a linear damper that doesn't depend on the deformation. We will have that in the instant before contact, the friction force is equal to 0, but in the instant in which we have contact, the force will be different from 0. This continuity is given, making the dependence on the deformation of the object we are entering in contact. So this overall system can be described by two different equations. One equation that is used in the non-contact phase, that is the equation that we had before, so a clamped free rotating flexible beam. But we have a different equation that describes the system in the contact phase. That is the equation in a flexible beam in soft interaction with the environment. So these two equations are basically different, and the principal difference that can be seen also from a practical point of view is that the beam's equilibrium in the non-contact phase is in 0 deformation, but the beam's equilibrium, the deformed case, in the contact phase is in a deformed configuration. It is possible to show that both systems are asymptotically stable. But the challenges that we have in this case is that first we have to show well-posedness of the overall system, and the well-posedness is in the sense that the solution is unique and it exists and depends continuously on the initial condition, is helped to be shown by since the nonlinearity is applied to the end effector that is part of the finite dimensional equations of the overall system, and so the nonlinearity doesn't act directly on the boundaries of the PDEs, and it is also helped by the fact that it's possible to show that the nonlinearity it's Lipschitz continuum. Then another challenge is the simple stability in the sense of Lyapunov, and it is the idea is to extend to the infinite dimensional case the Lyapunov stability theory that has been proposed by Branicki in 1998. This theory basically basically allow to have different Lyapunov function dependently on the active phase in which the system is in a certain moment. It also asks that every Lyapunov function is non-increasing in the system solution, along the system solution, and it also asks the so-called switching in condition. Basically, the switching in condition asks of having that the activation value of each Lyapunov function is lower or equal than the previous activation value of the same Lyapunov function. These three conditions are proven to be true for the system under study. Then asymptotic stability is still work in progress topic that we will investigate in the next months. So here I have the list of the publication. The first one is about the model of the double flexible manipulator. The second one is a publication that I didn't present in this presentation, and is modeling and control of an EPMC actuated flexible structure, a lumped port-Hamiltonian approach. And we basically use the port-Hamiltonian approach to control a flexible structure that is actuated by electroactive polymers. Then the third publication is the observer-based nonlinear control of a rotating flexible beam that will be presented in the IFAC World Congress, the virtual IFAC World Congress. And the last one is the stabilization of the rotating beam clamped on a moving inertia with strong dissipation feedback that has been submitted to the control and decision conference.